I think
All
you
right,
will
I'm
have to
going.
close out and play. Okay, good.
Nah, it's good. It's good. Okay, so if we go over a little recap of what binary exponentiation is, exponentiation is just like calculating something to an exponent. So if we wanted to do 5 to the power of 7, like, and write a program for it, you could just write a for loop from like 0 to 7 and just multiply 5 like repeatedly until you get it. But the time complexity of that's going to be like O of n, right? So in the case that we want to make a to calculate a power of like 10 to the 8th and bigger, which itself sounds kind of stupid, but there's other applications of binary exponentiation that go into like probability and stuff where you would need this optimization, and it'll tie into matrix exponentiation later. But as as you guys did in 17C, there is a log n way to do this as well. And the observation to do this in log of n is let's say we have some different power, like I want to start with an even one. So let's say we have like 4 to the 10th, then we can rewrite this as like 4 like squared to the 5th. Oops, wrong parentheses, kind of like this. And this way our power is cut in half, and we can do this multiplication in one operation. And because we're going to be cutting the power in half each time, the time complexity will be log n. The only time we can't do this is when the power is odd, in which case we'll simply rewrite it a different way. So we were to go through an example of calculating 5 to the power of 7 using binary exponentiation. um, we first need to notice that the power is odd, so we can't use that cut it in half trick. So we can rewrite it as 5 to the 6 times 5, and then now we have an even power to work with, so we'll rewrite it as 5 squared to the third times 5, and then this would just become 25 to the third times 5, and then same process, it's odd, so we have to subtract 1 from the power, so we have 25 squared times 25 times 5, and then here we square this, so 625 625 times 25 times 5, and instead of looping 7 times, we've essentially only done 3 steps. And if you multiply these three, then you should get 5 to the power of 7. So as for how we process this in code, essentially you'll notice whenever it's odd, we kind of reserve this power on the side, and then like we just leave it there to be multiplied in the end. But when we do it into code, it's a lot easier to just multiply into our answer, so we don't have to like push it into a vector and then iterate through all of the leftover odd powers instead. So what binary exponentiation ends up looking at as is you loop while your power is greater than 0, and then your result will start as 1, and it has to start as 1 because if it starts as 0, then anything you multiply would just go into 0, right? So while the power is greater than 0, if our power is odd, then we have to subtract 1 from the power, and we we know that we're going to have to multiply our current base into the answer. So once again, you can add it to a vector to do later, but it's just easier to multiply at that moment. So you do res times equal base, and then otherwise if it's even, if power is even, then you're going to square the base, so multiply it with itself, and then you're gonna cut the power in half. And then by the time you're all done with this loop, you'll have your answer. So are we all good on this? I
Yeah,
didn't
I'm
go
just gonna.
as in depth because we did it a while back. If you have any questions, let me know, or like when we get to the problems, you'll have a chance to figure it out and do it then. But essentially the breakdown is it revolves around this entire shortcut of when a power is even, you just square the base, cut the power in half. So you would rewrite this as 16 to the fourth. And in the case where the power is odd, like I don't know, like 9 to the 7, then you simply put aside this base. So you rewrite it as 9 times 9 and you subtract 1 from the power. So you split it off into this. And then because you know you're going to need to multiply this later, I just like dumping it into the answer at that moment.
So like when you have 9 to the 6, is like squaring it first and then cubing it going to be faster, or is cubing it first and then squaring it?
You're never cubing. Or
Yeah.
where do you mean by cubing?
Also, like when you have 9 to the 6, you rewrite that
Hmm.
as 9 cubed and then the entire thing squared. So like is it going to be faster to cube it first and then square it? Or like,
It's the other way around. So you're doing 9 squared and then you're changing the
oh,
power to 3. And the reason you do this is because you can calculate like 9 squared like in just one operation, right? You can just do base times base, right? So that would be this right here, and then you cut the power in half. But if you do it the other way around, then like where are you going to like calculate this 9 to the third in log n
uh,
time? Like if it's a bigger odd number than like 17, then like
mhm.
you can't like break that up very easily, right? So it's easier to square the base and then cut the power in half.
uh,
So in this case it's cubed, right? But like if I were to just make a different example, like I don't know, like 9 to the ninth, then it would be 9 times 9 to the eighth, and then now it would be 9 times 81 to the fourth. And then you just repeat until all of your powers are I say all of your powers, but it's mainly gonna be this one until this power becomes 0, and then
uh,
it should work.
all right.
So, yep, that's basically it. Are we all good?
Yep.
The Matrix Expo will get a little dank. So, we can expand this into solving linear recurrences. So, first, what a linear recurrence is it's anything where like the value of a number depends on like previous numbers in the sequence. So the easiest example is the Fibonacci sequence in which f of n, or actually, all right, like this, f of n is equal to f of n minus 1 plus f of n minus 2. And because this definition will never work for the first few numbers, for example, like if you're calculating the very first number, then how do you get the two ones before it? We have to make base cases. So in the Fibonacci sequence, I was telling Omar that some of them started off with 1 1, but I think most of them say that the first terms are 0 1. So um f of 0 is equal to 0, f of 1 is equal to 1, and then every other term from here on out will be the sum of the previous two. So this means that f of 2 is equal to f of 0 plus f of 1, so 0 plus 1 is 1. F of 3 is equal to f of 2 plus f of 1, so 1 plus 1, 2, and then it'll start growing very fast. So 2 plus 1, 3, and then if I keep just doing this without writing the ones at the bottom, you'll get this and so on. So it grows really quickly, but it's a sequence in which you form each number depending on some numbers before it. So what what usually we do and what I think you even do in CIS5 is you can write some sort of for loop to simulate this, right? So you can go ahead and have all of the values in an array, and then if you want to find the nth number in the sequence, you would just write a for loop from 0 to n minus 1, and then you would keep assigning you would go ahead and literally use this as if it was like array values, right? So like f of n is equal to f of n, or if you were writing it as a for loop, it would be I, so I minus 1 plus f of I minus 2. But the problem with this is this will take linear time because you're building them up one at a time, right? You're first gonna calculate so once again, I really should have just left the Fibonacci sequence up here. So if these are the first two numbers, you're gonna use these to calculate the next one, and then you're gonna calculate the next one, and then the next one, and then you're gonna do it one at a time. Meaning if you want to find the 10 to the 8th Fibonacci number, you're you're gonna need more than a second compiling in C++. So so there's a trick we can do instead. As it turns out, if we instead store these as matrices, there can always be a given transformation matrix or transition matrix, which will turn you from two pairs in the sequence to the next pair. So once again, I keep erasing these, so I'll draw them up here so I don't forget. So just let me draw out a few of these. Yeah, it should be enough. So essentially let's say we have like this pair right here, so 2 3. If we multiply it by like some matrix T, we'll call it, then it'll turn into the next pair 3 5. So turn into 3 5. And we can repeatedly take any single pair in the Fibonacci sequence and keep multiplying it by this matrix to get the next pair. So what I mean by this is we multiply this matrix into 2 comma 3 and we get the next pair. And if we do 3 5 multiplied by the matrix, we'll get the next two, which will be 5 8. So as for what this matrix is, you can use a little bit of linear algebra to solve it, but I like filling it in conceptually. It'll save you a little bit of time, and it'll also just make it easier to understand. For me at least. So so I'll just go ahead and say what the matrix is for the Fibonacci sequence. If the matrix is 0 1 1 1. So if we multiply this matrix by a matrix which holds two numbers in the Fibonacci sequence, so um like for example we'll do 2 3. If I multiply this into this will turn into 3 5. Uh, And if we want to try it, um, this row multiplied by this column, so you get 0 times 2 plus 1 times 3, and then you get 1 times 2 plus 1 times 3, and that just simplifies into 3 5. I don't know why I keep drawing this line, but it works, right? So we multiply this matrix into this, and then we get the next two numbers in the Fibonacci sequence. And because I said you can repeatedly multiply this matrix into it as many times as you want, we can simply if we wanted to find the next two after this, we could just square the matrix and then multiply it. So because now instead of linearly writing a for loop and then adding the next two numbers, we can literally take a matrix and then raise it to a power. Um, we can use binary exponentiation for this matrix instead of just an integer. So what'll happen is we're gonna do the same thing where if um if the power is even, we are going to square our matrix. If it's odd, then we're going to multiply our matrix into like our some answer matrix that we'll save for later. So so an important topic is remember how I said with binary exponentiation you need to start your result with 1, right? Because because if you start at 0, it's just gonna stay 0 because 0 multiplied by anything like is 0. So this concept seems very obvious, but it's actually very useful here. So the reason we multiply it or we initialize it with 1 is 1 is the identity element for multiplication. And what that means is if you multiply 1 by anything, like you get itself, right? It doesn't matter what it is. 1 times anything will be itself. So if we want to initialize our answer matrix, it has to be with some identity element of a matrix, right? Because we can't just fill it with zeros, because then the answer will never change. Likewise, if we initialize this with 0 and we calculate 5 to the power of 7 and we just keep multiplying 5, it will never change. So we need to know what an identity element of a matrix is. And an identity matrix is just defined as a matrix with zeros and 1 along the diagonal. So if you want an identity matrix of size 3, it would be 1 along the main diagonal, and then zeros everywhere else. So if you're going to do matrix exponentiation, you need to instead of initializing your answer with 1 in the case of an integer, you need to initialize it as an identity matrix. And then you're gonna go through the same process as binary exponentiation, where if the power is even, you square the matrix. If it's odd, you multiply this matrix into your identity matrix, and then you subtract 1 from the power and repeat until your power gets to 0. So that's the process, right? But how do we go about finding the transition matrix? Um, this is actually the hardest part, and I was stuck on this for ages, and it's really the only challenge of solving a problem with matrix exponentiation. So so we know that like if we have some like magic matrix that will get us the next number in the recurrence uh relation, then we can easily just like copy paste like code to square a matrix. But we need to have the right transformation matrix, right? So so the way that I kind of visualize making transformation matrices is you kind of write out what each cell means. So for example, if I rewrite the one for the Fibonacci sequence, you get 0, 1, 1, 1. So this bottom row will represent the definition for our f of n term, and this row above it will be what our definition is for the f minus 1 term. And the reason we have ones on this row is f of n is defined as f of n minus 1 plus f of n minus 2, right? So this column will be labeled f of n minus 1, and this will be f of n minus 2. And essentially you're kind of writing your definitions for each term across the row. So f of n is equal to 1 times f of n minus 1 plus 1 times f of n minus 2. The reason I want to make it important that we're putting ones here is the number that goes in the cell is related to the coefficient that goes in front of each of these terms. So in the Fibonacci series, it's just 1, right? The coefficient is just 1 for these terms, and such. We're only gonna have ones in the matrix. So f of n is defined as f of n minus 1 plus f of n minus 2, and then for f of n minus 1, f of n minus 1 would be f of n minus 2 plus f of n minus 3, but we can't like store this in a square matrix because like we only have a 2 by 2, right? But as we notice, like by definition, f of n minus 1 is like just itself. So we can put a 1 into here and then zeros elsewhere. So because f of n minus 1 just equals itself, if we were to say have like a Fibonacci series that depends on the 4 terms prior, you would notice we actually get a diagonal of ones across going from the bottom right to the top left after this first row. So if I instead expand the Fibonacci series to this, where you have to you have to add the previous four terms, then what is the transformation matrix? Well, at the very bottom row, we have f of n, the row above it, f of n minus 1, f of n minus 2, f of n minus 3, and we know that f of n is equal to f of n minus 1 minus 2 minus 3 minus 4. So if I label these columns, f of n minus 1, f of n minus 2, and then minus 4, we'll get 1, 1, 1, 1, and then f of n minus 1 is just equal to 1 of itself, and then 0 of everything else. F of n minus 2, you just fill in the 1 for the corresponding column, and then likewise with f of n minus 3. So this will be a very common pattern for making transformation matrices that are just like based on adding like previous terms. You'll notice you get ones on the bottom row and then you get ones on this diagonal. And if you didn't remember, the one for the basic Fibonacci series is just 0, 1, 1, 1 once again, two ones and then one on here, and then you would do it so on if it was dependent on more terms. So because these numbers represent coefficients, to make it a little more clear, I'll show you what would happen if you had different coefficients. So let's say instead you had f of n is equal to like 4 times f of n minus 1 plus 2 times f of n minus 2, and then 1 times f of n minus 3 plus, and then I don't know, we'll just say like 7. So what happened is you just have to change this bottom row, right? So so f of n is equal to 4 times f of n minus 1, so this becomes 4. Um 2 times f of n minus 2, so this will become 2. 1 times f of n minus 3, so we can leave this alone, and then 7 times f of n minus 4, so this will become 7. And the diagonal will stay the same, right? Because once again, these all equal like themselves. So this would be the transformation matrix if it were to be this instead. Um, are we still all good?
Easy.
Nice.
Right, Omar?
Yep.
Okay.
Screw you,
So
Omar.
I
Good
will
to play
change it a
around, Omar.
little. So at this part of the video, I made a mistake on the transition matrix for this recurrence relation right here. So if we go ahead and fill this out, this first row will be our definition for f of n. So we have 1 times f of n minus 1 plus 8 times n to the 0 plus 1 times n to the first plus 3 times n squared. So that's your first row, and then as I mentioned earlier, the part under it will expand to be terms of Pascal's triangle. So we had 0, 1, 0, 0, 0, 1, 1, 0, and then 0, 1, 2, 1. And that's the transition matrix for this recurrence relation right here. Some matrix that you've started with, right? So once again, if we go back to the easiest example of the Fibonacci series, so this is your transformation matrix for the Fibonacci series, and let's say you want to multiply it by some given term, or some given like pair in the series, like 8, 13. So if you want to get your answer, what you could do is you could literally just update this matrix by multiplying these two, but you don't always have to. And what I mean by that is like, I mean if it helps you, you can by all means just multiply this. But if you really think about it, the new matrix you get is 0 times 8 plus 1 times 13 for the top row, and then 1 times 8 plus 1 times 13. Therefore, it's 1321. You can observe that like if you want to get the bottom term, you can just add these two cells, and if you just want to get the term up top, you can just take the value in this. So I mean if you want, you could just form this new matrix and then just output what's in here, or you could just raise the transformation matrix to a power and then identify that, okay, the value in this cell will give me this element right here. Does that make sense? So you might have to do a little messing around with it in the problems, but that's essentially how you calculate your answer after you've risen the matrix to that power.
Yeah.
How did
Okay.
you do the math there with those two matrices?
Oh, how to multiply matrices? So
Yeah.
yeah, that's why I try to draw these or I try to write the steps out. So in order to multiply matrices, you just multiply like the row of the first matrix by the column of the second. So I do 0 times 8, so 0 times 8 plus 1 times 13, and so that will give me the result for the top row, and then you would do the same thing for the bottom one. So row times column. So 1 times 8, 1 times 8, plus 1 times 13. Um,
Yep.
it's just kind of how it is just how you multiply a matrix. If you need a refresher, you can always Google on
Google
it. Or yeah. Or if you or
matrix multiplication.
yeah. Have you taken linear algebra? If not, you
Uh-uh.
could it's pretty easy. You can just Google it real quick and you'll find it. But you can essentially think of it as taking the dot product between like this row and this column is all.
Okay.
So yeah. Okay. So I know it was a pretty tough topic for today, but I will switch to my screen now.
So for the case in which you were adding a constant, like I see how you could add another constant, like another column for the constant, but then like when you multiply it more than once, then doesn't that other value change? And then the entire matrix.
I actually did not follow that question if I'm being honest.
Oh,
Do you
yeah,
do you do you want to paint it or something?
um, I don't have my whiteboard currently. But yeah, I think I could.
Okay. But yeah, I don't know. I mean, I have some stuff on Symbolab, just to show that works. So this is the transformation matrix I showed you for that Fibonacci sequence that's dependent on the four previous terms. So if the first terms are just all ones, and we uh we we want to get the next four terms, so like slide it one over, it becomes 1 1 1 4, right? Because if we have 1 1 1 1 as the first four terms and each term is dependent by the sum of the previous four, we get 4, right, by adding these. And
Mhm.
if we add these, we get 7. So if you want to verify that that works, you can square this
Oh,
matrix and do that, and then you'll see we get 1 1 4 7. So yeah, that's
oh,
all. And then this is a very useful blog to I don't know, verify these things if you want. Once again, he talks about like throwing in constants in there and whatnot. But this is a cool blog to check out, so I'll send this
oh,
to you guys.
alrighty. So like for the
Oh yeah,
case
let me
which you had like,
hop in.
oh,
Just stop the recording? Or wait, let me see. Can I even wait, I cannot see your stream for some
oh,
reason.
oh, let me try sharing again.
Oh, it's a pop out. It's because I'm doing weird stuff with OBS.
Oh,
I'll just stop the recording. So
you could do like go on your computer and show what you're gonna show, and then I could like ask my question later.
yeah.
That
No,
works.
I think that's all. I'm gonna stop the
Oh,
recording.